first video for 5.3, connecting f prime and f double prime with the graph of f. This is really going to tie up a lot of things about derivatives and how they relate to the original function. So the first thing that you need to do is read over page 211 and 212 in your textbook, and I do want you to copy all of Theorem 4. Theorem 4 is the first derivative test for local extrema. So this is going to be how you use the first derivative to tell where you have those local mins and maxes. So there's one part on page 211. There's two more parts on page 212, and then they also deal with left and right endpoints, how to tell if you have a local min or a local max whenever you're dealing with an endpoint. So basically, if your first derivative changes from negative to positive, then negative would be decreasing, positive would be increasing. So if you change from negative to positive, you are going to have a local min. If you change from increasing to decreasing, that's a positive derivative to a negative derivative, then you're going to have a maximum. And that also includes at points where the derivative does not exist. Even if the derivative doesn't exist at a point, if before that you have a positive slope and after you have a negative slope, you'd still have a max, and the same with the min. With endpoints, if you have a left endpoint and the derivative to the right of that endpoint is positive, that means that was a minimum, because from that minimum it's going to increase. If you have a right endpoint and leading up to that, you had a negative derivative, that would also be a minimum. If you had a positive derivative leading up to that endpoint, then that would be a maximum. And the same thing back at the left endpoint, if you have a negative derivative right after that, then that was a maximum. And then you may have places where you have no change at all. Maybe it's something like a point of inflection or something else that's going on. If there's no change in sign in the first derivative, then your point that is your critical point isn't really going to affect your problem at all. So this does tie heavily with what we looked at in 5.1. So again, I do want you to copy that down so that you have that in your notes. And that leads us to this first example. This is part A. We are going to use the first derivative test to find the local extreme values, and then we're going to identify anything that's an absolute extreme. Now, this is a cubic function. And with cubic functions, you're always going to have one end going down and one end going up. This is a positive cubic, so the left end would be going down, the right end would be going up. There are no absolutes here because your arrows are going in opposite directions. So now, first derivative test, I do have to take the derivative, and I am going to set it equal to 0. So we have 3x squared minus 12. I'm going to set that equal to 0. I can factor out the 3. So whenever I set this equal to 0 and solve, or I can factor further and solve, either way would work. I get negative 2 and positive 2. So now I'm going to put that on the number line. So negative 2, positive 2, and I want to see what's going on with the sign of f prime. So if I take something, let's see, maybe negative 3 is one that's less, 0 is in between, 3 is one that's greater. And again, I'm plugging into f prime. So I'm plugging in to the derivative here. You can plug in to this part, or you can plug into the first part here. It doesn't really matter where you plug it in at. I would plug into what I underlined in green because you have smaller numbers to deal with. So if I have negative 3 squared is going to be 9, minus 4 is 5, times 3, well, that's going to be definitely a positive value. So that means, since my first derivative is positive, my graph is increasing up until negative 2. Now, I don't know what's happening after negative 2 yet until I plug in the 0 and plug in the 3. If I plug in 0, 0 squared is 0, minus 4 is negative 4, times 3 is also going to be a negative number. So that means after I reach negative 2, I'm going to be falling. Now we plug in 3. 3 squared is 9, minus 4 is 5, times 3, again, is going to be a positive. So then I'm going to be going back up again from 2 onward. So your local extreme values are going to happen where you change sign in the first derivative. Maxes occur where you change from increasing to decreasing. Minimums occur where you change from decreasing to increasing. So to state your correct answer in the way that this is asking for, we have a local max of something at x equals negative 2. Now to actually find that value, we would have to plug it back into the original problem. And we have one local min of something else at x equals positive 2. So to get those values, like I would have to plug negative 2 in up here. So f of negative 2, and you can trust my math on this one, is 11. F of positive 2 is negative 21. You can check that with a calculator if you want to. This is just going to save some time for the video. So we have a local max of 11 at x equals negative 2, local min of negative 21 at x equals 2. So this is part B. This one is not as familiar as the first one is. You may not recognize what exactly is going on here because this is not a polynomial because we are multiplying this by e to the x. So if you want to, if you're allowed to actually take a look at the graph, you can do that just to see if there would be any absolute extreme values. I do not believe this one does have any absolutes, so we don't have to worry about that. But we still have to take the derivative. This is a product, so we have to do the product rule. So the first times the derivative of the second, well, the derivative of e to the x is e to the x, plus the second times the derivative of the first, well, the derivative of x squared minus 3 is 2x. We are going to have to, we can factor out the e to the x here, and then we're going to be left with a trinomial that we're going to have to factor before we set this equal to anything. So whenever I take the e to the x out of here, I'm left with x squared minus 3. When I take it out of this one, I'm left with a 2x. So this is going to be x squared plus 2x minus 3 whenever I rearrange it. And then we're going to factor and solve this. So x plus 3, x minus 1. The e to the x is never 0, so that's why I didn't actually set that part equal to 0. E to the x is always going to return you a positive number. So negative 3 and positive 1 are the values that I'm going to be testing in my number line. And then I want to see what my signs are about the prime. So let's pick out something less than negative 3, like negative 4, something in between, something greater. I am going to plug this into this factored format down here because that's going to be the easiest for me to figure out what my signs are. So for example, negative 4, ignore the e to the x because that's always going to be positive. Negative 4 plus 3 is negative. Negative 4 minus 1 is negative. When you multiply two negatives, you end up with a positive. Plug in a 0. 0 plus 3 is positive. 0 minus 1 is negative. When you multiply them, you get a negative. Plug in a 2. 2 plus 3 is positive. 2 minus 1 is positive. When you multiply them, you get a positive. The domain here is all real numbers. There is no value that you can't plug in here. So because the domain is all real numbers, there's no real limiting factor on this other than it's probably not going to equal the negatives, but it's not going to actually bottom out at a value we can find. That's another thing that justifies the fact that there are no absolutes. So we're increasing up to negative 3. then decreasing down to 1, and then increasing from there on out. I guess in part A, okay, yeah, part A, I did do what they wanted there. I wanted to make sure they weren't asking, because this one doesn't just want the local and absolutes, it wants where this is increasing, where it's decreasing. So we have local max of something at x equals -3, local min of something else at x equals 1. You could plug those in, because for example, if you plug in 1, you're going to get 1 squared. Again, we plug into the original problem. 1 squared, which is 1, minus 3 is -2, e to the first. So this is going to be -2e. If we plug in -3, we have -3 squared, which is 9, minus 3 is 6. And then e to the -3 is 1 over e to the third, so this is going to be 6 over e to the third. The decimals for that, the top one is 0.299, and the bottom one is -5.437. So if you do see the decimals, that's what those are. And then we also have to state where this is increasing. It is increasing from -infinity to -3, and from 1 to infinity, and then we're decreasing from -3 to 1. And that would be all of the information that they ask you to complete for that question. Okay, so example 2, and I feel like we may have missed a slide here. Let's see here. So concavity, I don't know why that is not here. I'm going to just go back in and write this in. That's weird. It looks like it got deleted here somehow. So your concavity so if you have some function here, this area here is concave down, this area here is concave up, and then some point in between them is going to be your inflection point. That's where you switch concavity. So to tell concavity, where your second derivative is positive, it's going to be concave up. And it's concave down where your second derivative is negative. So there's a little bit more to this in the book. Again, I don't know what happened to my slide for this and why it's not in here. But for concavity, you're looking at the second derivative. Positive second derivative means concave up. Negative second derivative means concave down. So the concavity test from 3 to 10, we need to take the second derivative because you want to set the second derivative equal to 0 and then figure out where it's 0 because that's going to be the boundary again between your positives and negatives. So if I look at the first derivative here of x squared, that's going to be 2x. The second derivative is 2. Well, if your second derivative is a constant, that means that your concavity is always going to be the same value. And in this case, since 2 is a positive, it's always going to be positive, which means that this graph is concave up on 3 to 10. If it's concave up everywhere, then obviously from 3 to 10, it has to be concave up. Now, part B is a little bit different because we are dealing with a trig function. We are looking from 0 to 2 pi. So we are going to be using the concavity test again. So I want to take the first derivative. The 3 is going to drop out because that's a 0. So I get cosine of x. And then my second derivative is going to be negative sine of x. Well, if I set that equal to 0, on the interval 0 to 2 pi, x is 0, at pi, and at 2 pi. Well, 0 and 2 pi are my boundaries, so I'm not worried about what's happening before 0 or after 2 pi. But whenever I do my number line, I am going to consider those. So if I look at things that are happening in between, for example, negative pi over 2 and 3 pi over 2, and I want to know the sign of y double prime, if I plug in negative pi over 2, well, normally the sign of, I'm sorry, not negative pi over 2, this is just pi over 2. I don't know what I was thinking there. Plugging in pi over 2, sign of pi over 2 is positive, but because there's a negative out in front, that's actually going to be negative. 3 pi over 2, sign of 3 pi over 2 is negative 1, but again, there's a negative out in front, so that's going to be a negative. So because the second derivative gives me a negative value from 0 to 2 pi, this is going to be concave down, and it gives me a positive value from pi to 2 pi, so that's going to be concave up. So this is going to be concave up from pi to 2 pi, and concave down from 0 to pi. And again, if you're doing the AP exam and they ask for justification, you would say because the second derivative is positive for the concave up, and because the second derivative is negative for the concave down. Again, I'm not sure what happened with that and why it went weird. Okay, so this inflection point, the point where your graph changes concavity is called a point of inflection, and you can see here I did draw in. This one is changing from concave up to concave down. So that point in the middle where that happens, that is your inflection point. Your inflection point is where your second derivative is equal to 0 and where there is a change in sign in the second derivative. You may find places where the second derivative is equal to 0, but there is no change in sign, and that does happen occasionally, especially with like fourth degree polynomials that kind of look like quadratics. So just be aware, it's not just where the second derivative is 0, it's also where you have that change in sign in the second derivative. Okay, so this brings us to example 3. We want to find all the points of inflection of this graph, so I am going to have to find the second derivative. So your first derivative, so this is an e, so I would repeat, multiply by the derivative of the exponent, which is negative 2x, so this is going to be negative 2x e to the negative x squared. Now for the second derivative, we have to use the product rule. So that's going to be the first times the derivative of the second, which is e to the negative x squared times negative 2x, plus the second, e to the negative x squared, times the derivative of the first, which is negative 2. So this is going to clean up into a positive 4x squared, e to the negative x squared, minus 2 e to the negative x squared. I can factor out the e to the negative x squared, and I'm left with 4x squared minus 2. And again, that's what I'm going to set equal to 0. Now, we can ignore the e to the negative x squared because, again, that e is never going to be negative. This, though, I can set this equal to 0. And I get x is equal to plus or minus the the square root of 1/2, or plus or minus 1 over the square root of 2, whichever way you want to write that. So let's look at our number line here. So I have negative square root of 1/2, positive square root of 1/2. I'm looking for the sign of y double prime here. So something that's less than this, we can go -4. In between 0, greater, we'll go 4. So if I look at -4, and again, I'm plugging that into the second derivative because I want the sign of the second derivative. I'm going to ignore the e on the outside because I know that's always going to be positive. Because even though you have a negative exponent, again, that's not going to turn into a negative value. So we have 4 times -4 squared minus 2. Well, that's definitely going to give us a positive. 0, 4 times 0 squared minus 2 is going to give us a negative. 4 times 4 squared minus 2 is going to give us a positive. So we're concave up, there and there, concave down there. But this one doesn't say where's it concave up, where's it concave down. It wants the points of inflection. So these two are points of inflection, not just because the second derivative is equal to 0, but also because there is a change in sign in the second derivative. If you don't have that change in sign in the second derivative, it is not an inflection point. So we have negative square root of 1/2, positive square root of 1/2. If you plug those into the original problem, you're going to be squaring them. So you're going to get 1/2. Then you're going to get negative. So that's going to flip to the bottom. So 1 over e to the 1/2 power is going to be 1 over the square root of e. And it's going to be the same for both inflection points. So again, to find the y value of the inflection point, you would have to plug into the original problem. There's one more example that we're going to look at, and we're actually going to skip the next little part of this. So I do want you to read example 4 on page 215. If you want to try number 23, you can. Normally I would go through this as a class, but we're not going to be doing that today. That's a chart that goes through some of the intervals with what's going on in number 23. And so I want to talk about this, and this is going to wrap up our video for the first part. So again, this is what I've been cautioning the whole time. You cannot oversimplify the point of inflection by just saying it's where the second derivative is equal to 0. Because you could have second derivatives that are 0 at points that are not inflection points, like y equals x to the 4th. If you take the second derivative, yes, 0 will be the point that you get for the second derivative, but there is no change in sign at 0. And for example, your second derivative isn't always going to be 0. Sometimes it's places where the second derivative doesn't exist, like vertical tangents. So that would be where you have something like this, and then it comes up like that. That is a vertical tangent line that you have there where you're switching concavity, but the second derivative doesn't actually exist there. So again, the only safe way to test algebraically is to confirm the sign change of your second derivative. So make sure that you are doing that. Make sure that you are going through not just finding where the second derivative is equal to 0, but also testing that the second derivative changes sign. That's going to wrap up our first part video for 5.3. I know there's a lot of material in here, so this might have run a little bit long. So go back through, watch anything that you're not sure of, and reach out to me if you have any questions.